Okay, this question asks for a kind of an application problem. So suppose we have a vehicle that travels from the point A in land. So here this area is land. This area is water. So it travels starting from here and want to reach to here. So that's point A. That's point B. The speed of this vehicle online is the v1. So over here that will be v1, and over here will be v2. So now the question is, what is the shortest path, or the path that can the vehicle travels the fastest from A to B? So you need to determine this point so that the total time spent should be minimized. Okay, so since we know the speed of the vehicle on land and on water, so what we need to figure out is just the distance traveled. So if we call this length x, this total length is d. So that means total length is d. This is the x. That means this part is just the d minus x. So with the x, with the 1, we know the length here, which is the root of 1 plus x squared. Similarly, we know the length here. That will be just the root of 1 plus d minus x squared. Okay, so we know that these two lengths, and then we just divide them by the speed of the vehicle, and then we get the time over here and here, and then we can try to optimize this x. Okay, so that's the idea. The first question is to show that if we reach to the optimal x here, and then let's check the angle here, which is called theta 1 and theta 2. They want us to verify that the theta 1 and theta 2 satisfies this equation, where v1, v2 are the speed in online and water. So this is the one equation we want to verify when we reach to an optimal point x. The second question is, if the minimizer we found in the first part, in part A, satisfies the second order sufficient condition. So we need to check the Hessian there and see if so in this case you can see that it doesn't really have any constraint. The x must be somewhere in between. So we could expect that it's the interior point. So the second order sufficient condition is just to check if the Hessian matrix is positive definite or not. But if it's not the interior point, remember that we need to check that the Hessian matrix, when we multiply any feasible direction on both sides, we should get a positive number, right? That's what we do for when the minimizer is not an interior point. Okay, so let's check how do we do that. The first step, let's call this part x. So this x will determine where we're going to travel, right? How we're going to travel. So the x is the only unknown here. This is just a scalar. And see, as I mentioned before, we know the two distance, this and this, and then we divide their speed over the line and the water. That will be the total time, right? Because this is the time on line, this is the time on water. Okay, so that's the f, which is the time. So given x, this f of x will give us the time, total time we traveled. So if you want to find the minimizer, we need to check all the points that satisfy the first order necessary condition, and that means we need to take the gradient or take the derivative here in this case and set it to 0 and see what are the possible choices. So we take the derivative, and it's a little bit complicated, but still straightforward to compute, and then we get set it to 0 and solve for x. But for the first question, they just asked us when we reach to the optimal x, this equation should be satisfied. Okay, and let's just avoid computing x, since I don't think it's possible to compute x from this, too complicated. But we can just make a very easy arrangement, move this to the right hand side, and then keep v1, v2 over one side, and all the other things on the other side. So v1, v2, we can show that the v1, v2 in this case will be just equal to that, right? So since you move this to the right, and you multiply the v1 to the right and everything else to the left. So that's how we get. So we get this equals to that. But notice that this numerator is x over the root of 1 plus x squared. So that's this. So this is the x over root of 1 plus x squared, and that is exactly the sign of theta 1. Similarly, the denominator will give us the sine of theta 2. Okay, so that means when we reach the optimal point x, where the f prime equals to 0, we can show that the corresponding sine theta 1, theta 2 will satisfy this equation. So that's the first part of the question. Second part of the question is to check if the optimal point, which is the x, that satisfies this equation, also satisfies the second order sufficient condition. Okay, to do this, we just need to check the second order derivative. And second order derivative is nothing but just taking the derivative of this one more time, and then we'll get that, which is a little bit complicated, but we'll get to this eventually. And as you can see, no matter what x is always between 0 and d, right? Because that's how we chose the x. So no matter what that is, this is the positive number, 1 plus x squared. That's a strictly positive number, greater than 1, greater than or equal to 1. And this is the positive number 2, and that this is also a number greater than or equal to 1, and this is the positive number as well. So everything is positive, so we get a positive second order derivative of f, and that means the second order sufficient condition is satisfied.